For those of you just joining, give that one a try. See if you can use that technique we started yesterday, the elimination method. Choose one of the variables to eliminate. Get the numbers to be same size, opposite signs. Might say same absolute value, right? Same size x's or same size y's. I put one up there that I thought would be obvious, or that I would think there's an obvious choice. Which one to choose, x's or y's?
Good morning.
Good morning. We're working on this one, doing this one on your own as much as you can.
When you are ready for us to solve it, I would really like to solve it since I struggled so much yesterday. I think I've got the hang of it now.
So you got pretty far through your homework. Good for you. Yeah. Well, you want to tell us which variable did you choose to eliminate? That might be a good start for everybody.
I chose to eliminate my y's.
Yeah, I think that's I would have called that the obvious choice here.
So from what my tutor explained to me, that it's best to find something that has like a good common multiple, something that can go into each other really easily. Is that kind of the right method to go with?
Yeah,
okay.
Yeah, that's what I was trying to describe. You know, it takes time, I suppose, for the ideas to sink in and practice. But yeah, looking, you know, either the x's or the y's, which one would it be easiest to come up with? I would say the smallest multiple. You know,
yeah,
without letting the numbers get too big. Yes. So yeah, you can make 4s for the y's pretty easy. I think that was the point of this first example today. Yeah.
Oh, see, I made it harder on myself. I made them 8s. And that, see, there you go. There's, I don't think abstractly like that. Sometimes I go, oh, 2 and 4 make 8, so I can make an 8. I didn't even think, oh, it would have been much easier to have just made that 2 a 4, and I wouldn't have had to make 2 different equations to work with.
That'll still work, but yeah, even
I like to make things much harder on myself than they need to be, I guess.
I have a really quick question. So when we times all of it, do we times the after the equal sign too?
Absolutely, yeah. Right? You're doing
okay.
the same thing to both sides of the whole equation. Otherwise, you're creating a new relationship. It's got to be.
The way I write it out is I take that number I'm timesing it by and put it in parentheses next to like the 5x, and then it after the plus sign with the 2y, and then after the equal sign with the 21. I put that whatever I'm timesing it in there 3 different times just so I do the math properly, and I remind myself that that's how the equation is supposed to be done if I look back at my notes.
So that's probably the way I first presented it.
So I even put the 2 in the parentheses next to the middle.
Maybe could you wait and let me present a little bit? Okay.
Oh, I was just explaining that's how I do it. That's just the easiest way for me to understand if you were to write it like that.
So multiplying that whole first equation times 2. There you go. And now you went to 8s, so I'm just going to go to 4s. Hopefully you've all come up with something. I would think the y's were common. We're the easiest one there. There we go. So we have eliminated the y's that way. In both the elimination and substitution methods, we're looking for a way to take an equation that has 2 variables in it, pairs of equations with 2 variables, and somehow coming up with a relationship that reduces it to only 1 variable. We can't just solve it if it's got 2 variables in it. You know, that's a line. It's got an infinite number of solutions. So we're looking for that, some relationship we can build between the 2 of them. Dividing by that 17, I get there. So even with your 8s, Did you get to the 3? No. And as always in this situation, we need to find the other variable. So you could pick any one of those equations, but I'd stick with one of those that has the smaller values. You know, here we doubled everything. But put your x value in. Maybe I'll just use the first one, 5 times 3. Subtract the 15, right? What do we get there? 6. Divide by the 2. Well, it just so happened, x and y, I got the same values. Okay, there. Let my kitty out. Was there anybody who did something a little differently but still got there? All right, well, good first one. I'm going to put up another one then. One where I would expect you to need to multiply both equations by something. This kind of means we're going to end up with probably some big numbers over on the right side, but as one of the textbook problems, I'm trusting it's going to work out to be integer values eventually. All right, so there you are again, trying to figure out, do you want to use the x's? Do you want to eliminate the x's, or do you want to eliminate the y's? They're not really big numbers either way, but maybe you think one is better than the other for you. Caleb is saying the least common multiple. Think of what number is I usually like the idea of the smallest. What's the least common multiple you could get for the x's or for the y's? All right, I could get those both to be 15s. Or here I'd have to use 24s. It really doesn't matter. But in general, I like to keep the numbers smaller, so I probably would choose the 15s, which means we're going to eliminate the x's, or I would eliminate the x's. It'll turn out the same answer either way, assuming we make all the right moves otherwise. I like to get opposite signs just because adding a little less problematic usually. So it doesn't matter which equation, but one of them I would choose to multiply by a negative since they both started positive. Make one of them positive, one of them negative. Oh, my recent post about, well, 5.4, we're hoping to get into that, start looking at some applications today. I'll just, mention our tests scheduled for Monday. There's 10 of these problems, including a graphing one. And I've set it up as an hour and 15 minutes, a little extra time. Just make sure hopefully that's enough time to get through those 10 problems. A little longer. I cheated. Hopefully you've made a choice about what to multiply by. I'm going to do that step to my 2 equations here. I'm going to multiply this first one by 5 and this one times -3. Which one's positive, which one's negative, it's totally arbitrary. So here's that first one again. Now 5 times 67, oh well. Yep, gotta do both sides, huh? $335? Yeah. Okay. -3. Minus, right? We're distributing. And that one I can do, huh? -180. I'd say that's the hard part, is picking a good number to use to get them to be the same size values there. Oops, somebody waiting to get in here. There we go. The x's cancel. How about 31 y's left? And what's that number? Let's see, it's just subtraction. So 5, 13 gets me another 5. And 2 minus 1, 155. And yeah, it is positive. What do you think? How many 30s in 150, right? As a ballpark, but 31, I bet it's 5, huh? Yeah. Dividing by the 31, you get to use your calculator. I get a y value of 5. That's okay so far. Now we're going to plug that in, right? You define the corresponding x. Pick one or the other. I think use the second one this time. Slightly smaller y there value here. And be sure you find that original value there if you've kind of written extra stuff around it like I did. All right, 5x plus 15. If I subtract that 15, what do I get? 45. Ouch. X is a 9, huh? Divide by 5. So 9 and 5. Make sure you get your X and Y's in the right order there. Is that okay? Anybody else have problems with that process to get there? That was good enough. I'm going to put up a different one. Show us how to deal with some fractions if we've got fractions in them. Okay? So let's see. 1/3 x minus 1/2 y equals 1. 3/4 x minus y equals 5/2. This is similar, the recommended technique here. Similar to what I discussed in chapter 2 when trying to solve an equation that has fractions in it. You can work with the fractions, but especially in this situation with 2 different equations full of fractions, I would use that technique where you multiply by a common denominator for that one equation. Multiply it by something that will get rid of the fractions or make everything bigger enough so that they're whole numbers and not fractions anymore. Now, 2 different sets of denominators, 2 different equations. You don't have to multiply both by the same thing. You're just trying to change one equation at a time. So, just looking at that first equation, look at the fraction values and say, what's the common multiple? What's the common denominator I could use and multiply everything by, and then it'll cancel out the fractions. Right. Hopefully 6 looks pretty obvious there. So I'm going to multiply every one of those terms. This is not even trying to get the same size coefficients yet. This is just getting rid of fractions. So it's another layer of work. So I'm going to multiply everything by 6. And If I do that, 6 times 6, and then even the whole number has to be multiplied by 6 over there. Now I'm going to write it out. If I do 6, I get 6/3 over x minus 6 halves over y equals 6. All right. Now that will reduce, right? Simplify that fraction. 2x minus 3y equals that 6. I'm going to write that over here out of the way now, okay? 2x minus 3y equals 6. So there I've just changed that first equation. Doing a similar thing to the second equation. Look at the fractions. 4 would be a good common denominator, the least common multiple, right? The smallest number. So if I multiply everything times a 4, again, I'm going to write that all out. So 3 times 4 is 12/4 minus, and that's just going to be 4y. Now over here, I'll get 20 halves, right? So I chose that number carefully, I'd say, so that these should simplify the whole number. So I get 3x minus the 4y didn't change, equals 10. So then I'm going to just write that one over here now also. Got rid of the fractions from that one. This is totally equivalent to the original system. Both equations have just been made like proportionally bigger. The relationship within each equation is still the same as it was. I'm just now looking at fractions. So now we're where we've been the last example or two. Now we can think about which variable to get the same coefficients on, same size numbers. Do we want to get x's? Looks like we could turn the x's into 6's, or we'd have to go to 12's for the y's. Why not use the 6's, the smaller, right? I'm kind of done with all this stuff over here now, okay? But I'm going to try to work over here on this side of the board. And I'm really kind of doing that, right? So let's see, if I want to make them 6's, right? You're going to make them 6's, you're going to multiply that whole equation. Here, I'm going to kind of cheat and say that's going to multiply by 3. The whole equation by 3. I want opposite signs. I'm going to choose this whole equation times -2. Both sides, right? So that's why I say I'm sort of cheating. I didn't just squeeze it in over here. This 3 is going times every term, both sides. All right, put it over here in your notes, okay? That's probably better anyway. Put it on both sides in your notes. So now 3 gets me 6x minus 9y is 18. And -2 gets me -6x minus plus 8y, -20. After getting rid of the fractions, this is exactly what we've been doing for a while now. Adding them together, x's cancel, -1 is -2.
Can you slow down just a little bit, please?
Yep, okay. Wait for me. It's okay. If -y is -2, then multiply both sides by -1, you get that y equals 2, huh? Now I have to find my x's. Now here's where I was sort of preparing for this kind of situation where I was saying you can use any one of the equations that's been derived from the original equations. I could use either one of these first two equations and plug in a y value of 2. But I'd still have the fractions to work with. But either one of those two that I've gotten rid of the fractions from is equivalent. I would recommend choosing one of those two to plug the y value into to find the x. You know, why mess with the fractions if you don't have to? It's kind of the idea there. Picking either one, let's just say the first one, 2x minus 3 times the 2 equals that original 6 up there. 2x minus 6 is 6. Add the 6. Divide by 2, x is 6. To get that, x is 6 and the y was a 2. So the point of this example was that technique there of multiplying to get rid of the fractions. And I mean, you could think about it and say, well, I could really just try to double this one and then I could get rid of the y's, but you know, then you'd be trying to add a bunch of fraction x's. It's messier. You do think that's cleaner and less prone to mistakes. I think there was one like that in your homework. All right, let me know if, do I need to wait? Should I wait? Okay, well, I want to address, remember those 3 different possibilities? You know, one solution is pretty normal for 2 independent lines, right? A consistent system, but sometimes they were parallel, and sometimes they were the same line. Well, we can figure that out from the equations. I'm going to make up a couple examples here to kind of show how that might work. First of all, let's say I do a system that looks like this, and I'm trying to make it kind of obvious, right? Hopefully. We're kind of at this point now, unless a problem asks you to use the elimination or substitution method, you get to choose. Usually one of those 2 different methods to solve it. I would not recommend relying on the graphing method unless it was set up to be a graphing problem and you knew the numbers were going to work out nicely. So this looks like one of those problems we did in 5.2 where the substitution method would work pretty well. They're both already solved for y. Just look what I did, just try to make it clear to begin with. Those 2 have the same slope. We know those 2 lines will be at least parallel and possibly even the same line. Well, just the fact that they have different intercepts, we know they're not going to be the same line. So this is an example of 2 parallel lines. Now, what would happen if I tried to use one of our 2 recent techniques to solve this? I'm going to use the substitution method. That is, I'm going to say, take this and put it over here in there for the y. If I do that, do the substitution, here's that expression, and here's that other side of this one. So there's an equation that has just x's in it. Parallel lines, right? So we expect something's going to show up. That means those are parallel lines. Well, if I subtract the x's from both sides, I get down to one of those those false statements, right? 3 is equal to -5. This is a contradiction, right? It's not equal to -5. There is no value for x that would work in both equations. They would never meet. We get, or even if I went farther, sometimes remember some 0 equals -2. If I tried to subtract, it would actually be what, -8 if I subtracted the 3 from both sides. 0 equals something other than 0. So this is no solution. This is what happens to the equations. We're just trying to work with the equations for a situation where the lines are parallel. You get down to this. Notice there's no variables left in that statement, right? No variables. Now that, I made up one. You know how I've said, I usually try to hide it so that the 2 forms are slightly different and you don't immediately recognize that they're same slopes. If you're doing your work, it'll eventually boil down to something like this. But I started with kind of something obvious so we could see maybe where it was going. Here's one, another system. And this one is set up in that other form where the elimination method often works better than substitution. Let's put it that way. If I was trying to solve for one of those to use substitution, I might have to solve for y as the easiest, moving the x's, then dividing by 2, I'd get fractions. I think this elimination method would work pretty well with this problem. In particular, this really doesn't matter much. Let's say I'm gonna multiply that top equation by 3, okay? I'm gonna multiply this whole equation times 3 so I could get -9 and +9. 3 on both sides, okay? So here goes that. Rewriting, -9x plus 6y equals what, 24. All right, this is what's happening, the same situation, right? X's are the same, so when I add, the x's are gonna go away. But the y's are the same, but opposite signs, so the y's are gonna go away. And I get, again, one of these false statements. So using the elimination method, you still get down to this kind of statement, right? Just like the substitution example for parallel lines. Okay, if your substitution or elimination work with just the equations, no pictures, right? If it boils down to something like that, that's a no solution situation. What about those dependent equations? Two equations that are actually the same line, right? Now, both of our techniques are used to eliminate one of the variables. And if you remember our equation solving where we had two equations that were the same line, we got to something looks like 0 equals 0, always true. So the same thing's going to happen here with our systems of equations. Again, let me just kind of make up a obvious one, and I mean, you won't even see them like this, but just to see how the technique would get you there, right? Obviously, those are the same equation. I wrote them on purpose to be the same equation. Now, maybe one of them would be in a different form, and you'd have to do a little more work to get to this point. But if I did that same thing where I substituted right, careful, right? Obviously, but if I subtract the x's, 4 equals 4, well, yeah, that's always true. Or if I subtracted the 4s, get to 0 equals 0, that's always true. No matter what the variables are, those are the same line. But this is what happens to your equations when you combine them through substitution and boil it down. You're going to get down to a always true statement with no variables. Same lines. Dependent is that they're tied to each other. Dependent equations, infinite number of solutions, right? Now, a similar thing can happen. Oh, let's say, can I make up one here? Just looking at those numbers, without trying to make it too tricky, you recognize just any relationship off the top of your head between those two equations. one equation happens to be a multiple of the other equation, right? I just made it up as all these numbers are just double the other one, like I multiplied the whole thing by 2. If I multiply this whole equation times -2, right, and use my elimination method, they all cancel out. And I still get to that kind of statement. Again, for dependent lines, the same lines, it boils down to a always true without variables, 0 equals 0 kind of statement. So that's what happens for dependent lines, same equations. So when you're working through, you know, your homework, I saw some of the mom problems, you know, they gave you those multiple choices, right? And if it was one solution, you have to fill in what the solution is. And then they had choices like infinite solutions, which would be this situation, or no solution. And you were able to just check that box. And you're kind of done. No solution. 0 does not equal 5. And you're done with that. So just sort of explaining how that works out. And when it happens, you hopefully will be able to remember that or refer to your notes. All right. Now 5.4 is all applications. Each section's been ending with a little bit of applications. How about something like this? In this elimination section, there are questions that are kind of, well, this shape, huh? The sum of 2 numbers is 65. Their difference is 25. Find the numbers. Okay. So we need 2 different conditions is really what it boils down to. If we have a system of 2 equations, 2 different variables, we need 2 different relationships so we can use to put them together. Right, 2 equations. Here's examples of equations that'll fit nicely into that x's and y's on one side and the constant on the other. Excuse me. Might say something like, let x be the larger, right? If their difference is 25, one's bigger than the other. And let y be the other, something like that, you know. Defining my variables. I'm defining variables. I'm going to use x and y in this problem. So I have 2 numbers. This one says the sum of those 2 numbers is 65. The sum of these 2 is 65. There's the information to write one equation. Right? Add them together. X plus y is supposed to equal 65. Hopefully that's pretty clear. You get that out of there. Their difference is 25. Well, and so one minus the other, right? And so since I'm calling the x, I'll start with the bigger one. I'll start with the x and say x minus y equals what? 25. Ta-da. Isn't that kind of nice? Nice system, easy system, right? It's ready to go. Go to work, add them together. See how the y's are ready to eliminate each other. Is that 90? It's the next x of 45. And as always, if we're looking to find both numbers, plug it back in and say, oh, let's just say here 45 plus y equals 65. Subtracting the 45 must be y equals 20. Now this is a kind of problem, unless the problem tells you to call, like I did, one value the x and the other a y, it might not ask for an ordered pair, but just describe the 2 numbers or give them in descending order, right? List the biggest one first or something like that. But here hopefully we know we got a 45 and a 20. however you're asked to present that answer. Just be careful, read the instructions carefully. So there's an example of a kind of problem where all the information works together on the left side of the equation and adds up to something or has a difference of something. And you can build this kind of system where the elimination method actually tends to work pretty well. Okay. I'm going to do another one like that, okay? Similar construction, but different story up here. This one is just, you might call them number problems, where they define a relationship without a whole lot of extra context. And, all right. A person is doing some shopping, right? 3 shirts and 2 sweaters cost $114. 2 shirts and what's my numbers here? 4 sweaters, yeah, whatever, made up problems, cost $164. Find the cost of shirts and sweaters. Squeeze it in. 2 different relationships between the 2 unknowns. So we can use each sentence to build an equation. What is it we're looking for? What do our variables stand for? They stand for the cost or value of these 2 different items. So it's unfortunate they're both S's, so I'm going to use X's and Y's again, okay? But sometimes you might say, oh, S for shirt and P for pants or something. Use a variable. Just pay attention, Mom sometimes tells you what to use. Let's say, let X be the shirt price. And therefore I will say, let Y be the sweater price. Okay. So this time it's not quantity, but cost, or the value of these items. All right, so now I want to write 2 equations using my variables based on those 2 situations. All right. Our cost, that's going to be that total number they have equals, it equals this amount. This one equals that amount. It adds up. The cost adds up to that. Well, 3 of that cost, right? 3x, funny 3, sorry, plus 2 y's, supposed to equal that amount. This one says, 2 of the x's plus 4 of the y's, supposed to equal that amount. You seeing how I'm pulling that out, building those from that information. There again is that form with the x's and y's on the left. Numbers aren't too complicated or messy. We could use our elimination method again. These are both examples these last 2 examples that came out of that elimination section of our chapter. Probably see similar in 5.4. Out of the textbook anyway, I'm taking these out of our textbook. I'm going to erase the top so I can work that problem, okay? Just erase the story here. Hopefully, assuming you copy that down if you wanted to, all right? Here goes. Give me room to work. But let's say as I recopy them, I could turn those into 6's, but I could make those both 4's, right? How about if I multiply this whole first equation times -2, right? So as I rewrite it, -6x minus 4y equals negative 228. The 4 is already there, so I'm just recopying this one. 2x plus 4y, 164, yeah. And that elimination method is going to work there for the y's to be eliminated. Negative 4x equals, this better be negative, right? Is that another 64? Let's see. 4 and yeah, negative 64. Divide by the negative 4, 16. Now here's a kind of problem where there was a context. X is not just this number 16. What does X stand for? In class paper tests, you'd be given instructions to write a complete sentence. Right? Shirts cost $16. That's what that means, right? Units there. Now I need to figure out the sweater price. Pick one of those equations. Let's see, I think I'll just use this, okay? 2 times 16 plus 4y equals 164. More room here, okay? So what is that? 32. Subtract the 32. And 4y equals 132. Divide by 4. Y equals, what is that, 33? Yep. Sweaters cost $33. So a couple of situations that work out well for the elimination method, applying that elimination method. And I want to find one of my other examples here. Bring it. Probably 3.4. Okay. You know what, folks? I'm going to stop here. We've got all day tomorrow just to deal with more of these applications. Okay, 3.4 in particular is going to present some MX plus B type shapes. And another one, I got to find my preferred examples for ones that sort of a combination. It's often like a ticket problem. They sold adult and children's tickets, how many tickets, and how much money did they make? Sort of a combination of quantity and value together. Get that one ready for us. But
Question after class. Can I stay for a minute and ask you?
oh, okay, yeah. So that'll be it for today, folks. Come on back tomorrow and we'll keep plugging away with some applications, some more applications. All right, thank you all. And you're all free to leave, but I'll here wait for
Thank you.
Thank you.
yeah. Yes, you're welcome. What's up?
There's another person still.
Hi, Derek. You wanna? Are you there, Derek? Maybe he's not even at his computer. Is this
Well,
personal or
Huh?
is this personal?
Yeah.
All right. You want to let's see.
You can unrecord.
There, that's